Welcome back, guys. Today we're going to continue our lessons on relations and functions. And today specifically we're going to be looking at functions, which are just a special type of a relation. In our last lesson, we talked about the definition for relation being the comparison between two objects. And so that could be looking at distance versus time, or the position on a Ferris wheel over time, and so on. And today we're going to be looking at functions. When we were representing relations yesterday, we were looking at things like table of values, coordinates, representing relations using mapping notation. And so now you might be wondering, well, what's a function? And so let's take a look at that definition. So a function is a relationship between inputs and outputs where there is only one output for every input. So yesterday when we were looking at relation, we were talking about how the input related to the output, but we weren't specific about how many outputs or how many inputs there could be. When we're looking at a function, there's very specific information that we need, and that's that there can only be one output for every input. And so if we think about a function, we could think about a function as a type of machine. And so if I were to look at a function, for example, x plus 2, I would put that function or that rule inside my machine. And then for every input that I put in, I should only get one output. So for example, let's put in a 4 here, and we'll plug this into our machine and let it do its work. Beep, 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 boop, 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 beep. 6. All right, so we plug in a 4, and 4 plus 2 gives us 6. If I try a different different input, I would plug in, for example, I might plug in 0, plug in a 0, let it work through the machine. Beep, 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 and we get 2. So plug in a 0, 0 plus 2 is 2. All right, so let's take a look at some examples of what is a function and what's not a function. So first of all, these are examples of functions. And then these are examples of non-functions. And so the first column here, or the first section, is functions. And the left-hand side is not a function. All right, so if you look on the left-hand side, we've got a table of values. We've got 3, 2, 1, 2, and 3. So there's only one output for every input. Versus if we look over at the table on the right-hand side here, we have a -1 and 5, and we have a -1 and 8. So we have two outputs for the same input. Another table of values here, we have 2 2s. So we've got two outputs, or two inputs, two inputs that are the same, and so that's leading to two different outputs for the same input, not a function. If we look at mapping notation, on the left-hand side, P goes to M, Q goes to N, R goes to N. It's okay to have two different inputs go to the same output, but on the right-hand side, if we look here, we cannot have two different outputs for the same input, so this is not a function. If we look at a graph, a way that we can tell if a graph is a function or not, we can do what's called a vertical line test. And so if I draw a vertical line a vertical line through that graph, if I only cross the graph in one spot, it is a function. If I were to look at this graph here, no matter where I draw that vertical line, if I cross the graph in more than one spot, it is not a function. Now, if we look at equations, when we're looking at an equation, what we don't want to see is we don't want to see a y squared. So we just want to see a y with an exponent of 1. And so y here, y to the 1 is 4x squared minus 3. That is a function. Y equals root x. That is a function. Versus the other side here, we've got a y squared, not a function. And y squared equals 3x, not a function. All right, so we're going to take a look at these a little bit more specifically. So first of all, we're going to look at the vertical line test. And so if we were doing the vertical line test, like we said before, you're just going to draw a vertical line through the graph at any point. And as long as nowhere on that graph you can draw a vertical line and cross more than once, then it is a function. So if we're doing a vertical line test, essentially what we do not want is we do not want stacking x's. So we're going to say no stacking x's. And so if I look at this first graph here, no matter where I draw my graph, where I draw my vertical line, I only cross the graph in one spot. If I draw a vertical line through the next graph here, no matter where I put that line, on the graph, I am only crossing the graph in one spot. And so there'd just be the 1x right there where it crosses. Now, if I take that vertical line and I draw it through the last graph here, I draw through and I actually cross that graph in more than one spot. And so this is where we get those stacking x's. So I've got 1x here and 1x here. So if I cross the graph in more than one spot, it is not a function. So this would be a function, this would be a function, this is not a function. All right, another way to identify functions is to look at ordered pairs. And so what we don't want to see is any repeating x's. So no repeating x's, which is similar to the one right before, because if I were to graph these on a graph, I would have two inputs. Two of the same inputs would lead to a failing of the vertical line test. And so here, the first one, I've got 0, 3, 1, 4, 2, 5. This is a function because there's no repeating x's. If I look at the next table here, I've got 0, 1, 2, 4, 4. Oh, there's a problem right there. Same two inputs, so this is not a function. The other table of values, we've got 0, 2, -2, and 5. There are no repeating inputs, so this is a function. And the last one, we've got 1, 7, 1, 8. Oh, right there's a problem. We've got two of the same inputs. This is not a function. All right, now the last way to determine if something's a function is to look at the equation. And if we're looking at the equation, we want no y squareds. So the first example here, we've got y equals x squared. This is good. That's a function. X equals y squared. No good. This is not a function because we've got the y squared. Next one, y squared equals 2x plus 1. There's our problem. This is not a function. X equals y squared. Again, we don't want any y squareds. This is not a function. And then y equals square root of x. This is good. It is a function. And so if you wanted to test these out, you could graph them on your calculator and see if they pass or fail the vertical line test. Here's the thing. If you want to try to plug x equals y squared into your calculator, you know that your calculator is y equals. So you'd have to enter these as two separate equations. Your calculator can only graph functions. And so if you can't graph it on your calculator without having to split it into two equations, that's also a hint that it's not a function. All right, so we're going to move on to function notation, which is a different way to represent a function. And so you're familiar with the equation y equals 3x plus 1, but we can also represent that as f of x equals 3x plus 1. So again, our equation is y equals 3x plus 1, and we're going to change that to f of x equals 3x plus 1. And if you notice, the only change that was made, originally I had y equals 3x plus 1. All I did was take that y and replace it with something called f of x. And so this is a notation you've actually seen on previous assignments, but may not have recognized it as anything different. The only change is that we've replaced the y with an f of x. But the f of x actually is more valuable because it can give us more information in the graph. So we're still dealing with x and y, it's just that now f of x represents y. And so f of x is what's called the name of the function, and it's read as f of x. It is not f times x. So it's read as f of x. If I wrote an h with the brackets and x, that would be read as h of x. If I wrote a g, it would be written as g of x. And that's just saying that h is a function of x, or g is a function of x. And the x value represents our input. And then the other part of the equation, the 3x plus 1, would represent the function, but it'll also give us our input. So how do we use function notation? Well, when we have an input of 2, we write f of 2, and then that 2 tells me to now, or that f of 2, I know my input is 2, that tells me that in the function, I'm going to replace the x with a 2. So now I have 3 times 2 plus 1 equals 7. If I have f of negative 4, my original function was 3x plus 1. I'm going to take that input of negative 4 and substitute it in for my x, and I have 3 times negative 4 plus 1 equals 11. And so my input is 2, and my output is 7. And so sometimes you'll see this written this way, f of 2 equals 7. That means my input is 2, my output is 7. Or f of negative 4 is 11. So my input is negative 4 and my output is 11. When we just write the equation y equals 3x plus 1, we can't get that same information. So the function notation is something you'll see quite frequently in high school because it gives us more information about the function. All right, so let's take a look at some examples here. So the first question says, write x plus 4 in function notation. So we're literally just going to take that y and replace it with an f of x. And so our function, and you'll notice I'm writing it with a scripted f. You could just use a regular f, but typically we see it as a scripted f of x equals x plus 4. So that's all we're doing is replacing the y with an f of x. So if we're going to use function notation, the first example here says use the functions below to determine the given input values. So if the function is f of x equals 2x plus 4, and we're being asked for f of 3, all we're going to do is take that 3 and put it where the x is. So 2, and whenever we substitute, we use brackets. So 2 times 3 plus 4. So 2 times 3 is 6. 6 plus 4 is 10. So this is basically that 2x plus 4 is like our function machine. We're plugging the input in, and if you want to make the little computer sounds, go for it. But we're just plugging that in and then getting our answer. So we could write our final answer as f of 3 equals 10. All right, so if we've got f of negative 5, we're going to have the 2. We substitute our input with negative 5 plus 4. And so f of negative 5 equals negative 10 plus 4. F of negative 10, or f of negative 5 equals negative 6. All right, we'll take a look at one that is not linear. So we've got 5x squared plus 8. Now you might be saying, well, how do you know it's not linear? If you remember from our last unit, or our last topic here, if we saw anything that was, if we saw any input that had a degree higher than 1, or an exponent that was higher than 1, then it was not linear. So 5x squared plus 8 is not linear. In fact, it actually looks like this when we graph it. So if we substitute in g of negative 1, again, that negative 1 is going to go in for the x. And this is where brackets are extremely important. Anytime you're dealing with negatives, those brackets will make a difference. So it's important that you get in the habit of always using brackets when you're substituting. So 5 bracket negative 1 squared plus 8. If we didn't use those brackets, we'd miss squaring the negative. And so we have 5 times 1 plus 8 equals 5 plus 8 is 13. So g of negative 1 equals 13. All right, g of 2, we're going to have 5 times 2 squared plus 8. 5 times 4 plus 8 will leave us with 28. So g of 2 equals 28. Now, up to this point, we've been just substituting in numbers, but we can substitute in letters as well. So if the statement says, if f of a equals 2a squared, what is f of x? Well, we do the same thing we did with the numbers. We replace the x, or the a, with an x. So we would write f of x equals 2 times x squared. For f of m, we'd have f of m equals 2 times m squared. What about f of b? F of b is 2 times b squared. And then the last one, it says f of x plus 1. Well, f of x plus 1 would be 2 times x plus 1 squared, which you could multiply out if you chose to, but we could just leave it like this as well. 2 bracket x plus 1 squared. All right, so we can also work in reverse. So we can be given the value of f of x and then work towards solving for x. So in these questions, it says if f of x is 3x minus 1 and f of x is 14, what is the value of x? Well, we've been told that f of x equals 3x minus 1. We've also been told that f of x equals 14. So that means these represent the same value. So we're going to take that 14 and we're going to substitute it in for f of x. So we're going to write 14 equals 3x minus 1, and then we're going to solve for x. So to get x by itself, we're going to add 1 to both sides, and that gives us 15 equals 3x. We're going to divide by 3, and x equals 5. Okay. And then we could always go back and double check if we wanted to. We could plug that in. We could plug in f of 5. F of 5 is 3 times 5 minus 1. Well, 3 times 5 is 15, minus 1 is 14, so we know that we did it correctly. Next one, we have g of x equals 5x squared plus 1, and g of x equals 501. So we're going to have 501 equals 5x squared plus 1. We're going to subtract 1 from both sides. Gives us 500 equals 5x squared. Divide by 5. And that gives us 100 equals x squared. We're going to square root both sides. Now, when we square root, we have to remember plus or minus. So when we square root 10, we get plus or minus 10, when we square root 100, we get plus or minus 10 equals x. So that means we have two values. That means that f of 10 equals 501. It also means that f of negative 10 equals 501. And again, you could double check those. You could plug in the 10 or the negative 10 and check to see that you get 501. So in this case, we've led to two answers. All right, so I'd like you guys to try a couple on your own here. Take a look at the questions, pause the video, try them for yourself, and then come back and check your answers. All right, welcome back. So we're going to start off by writing out our equation. 5 equals 2x plus 1. Again, remember that the h of x is the same value, so we're just taking that 5 and we're substituting it in. So 5 equals 2x plus 1. We subtract 1 from both sides. That gives me 4 equals 2x. We're going to divide by 2 on both sides. And we get x equals 2. And so that means that f of 2 equals 5. For the next one here, we've got f of n equals 7n minus 3 and f of n equals 10. So it doesn't matter what letter I've used for my input, we just see f of x more often. But whether it's an x or an n or a p or a q, doesn't matter as long as whatever our input is, whatever our input or output is, are put in the correct positions. So here it says f of n is 7n minus 3 and f of n is 10. What is the value of n? So it's the n value that I'm looking for. It's quite common for people to mix up n and f of n in these questions. Just look to see what looks the same, and you're only substituting into things that look the same. And so we're going to have 10 equals 7n minus 3. Our first step is to add 3 to both sides. And so that gives us 13 equals 7n. And so we're going to take our 13 and divide by 7. Let's move the screen down here. Take our 13, divide by 7. And this will give us a decimal, so we're going to leave it in exact form. So x equals 13 over 7. So f of 13 over 7 equals 10. And so again, you could check that on your calculator. You could take the 13 over 7, multiply by 7, and subtract 3, and you should get 10. All right, so we can also do function notation with graphs. And so if you're looking at function notation and you're looking at a graph, basically you're being given either the input or output, and you're just looking on the graph to get the other, to get the one that you're looking for. So for here it says, using the graph of f of x, state the value of the following. So the first one says f of 2. Well, 2 is our input. And so if we're looking for f of 2, we're given an input of 2, so that would be our x value, and we're looking for our output. So if we have an input of 2, our output is negative 2. So f of 2 equals negative 2. If we're given f of 1 is right here, so f of 1 equals 0. So our input is 1, our output is 0. So then we're told f of x equals 2. Well, this is our output. So this represents our output. So if we have an output of 2, we're looking for x, which is our input. So this time we have an output of 2. So that means a y value of 2. Our input is 0. So f of 0 equals 2. So that means x is 2. For the last one here, it says f of x is 4. What is x? Well, this is an output, and an output of 4 has an input of negative 1. So f of negative 1 equals 4. So x equals negative 1. I'll give you another graph. Maybe pause the video, try this one on your own if you like, or just follow along. All right, so here it says using the graph of t of h. So again, it doesn't matter whether it says f of x or p of q or anything like that. It just matters that we know this represents a function. Often you'll see that the letters represent the context. In this case, we're dealing with temperature and time. So h is representing time and the t is representing temperature. So temperature as a function of time. So we're asked for the following. So t of 1. So our input is 1. When our input is 1, our output is 80. So t of 1 equals 80. T of 3. So what is the temperature when the time is 3? Well, temperature when time is 3 is 76. Sometimes when we look at a graph in context, it makes it a little easier to see how that function notation is working. And so T of H, so temperature as a function of time is 72. So this is our output value here. So this is our temperature. So when we have a temperature of 72, our time is 5. So H equals 5. And if we have a temperature of 82, so a temperature of 82, our time will be 0. So H will be 0. All right, so we're going to look at one more example, and this actually is going to give you an opportunity to review some of the things that we did in the previous unit. So function notation is the new piece. The linear functions part is just going to be an example to help you refresh your memory from our last unit. So we're given some information here. We're told that f of x is a function, and then we're told some inputs and outputs. And the question is, does this represent a linear function? And if it does, then we're going to write that function in general form. Now I'm giving you a heads up right away. It is going to represent a function, a linear function, but let's find out why. So the first thing I'm going to do is I'm going to make a table of values. So when we're given function notation, it gives us lots of information, but we'll get a better visual if we write this out in a table of values. So if our input is 3, our output is 5, our input is 5, our output is 6, input is 7, output is 7. So if we think back to our last unit, if we want to determine if this is a linear function, we want something that's in the form y equals mx plus b, the first thing we got to find is our slope. So we're going to pick two coordinates. I'm going to choose 3 and 5 and 5 and 6. And we're going to find the slope. So slope is y2 minus y1 over x2 minus x1. So 6 minus 5 is 1, and 5 minus 3 is 2. So our slope is 1/2. Now from there, you can use either method. You can use the point slope form or the slope intercept form to find your b value, but ultimately we need to know what b is. So I'm going to choose the 5 and the 6 here, and I'm going to put y equals m, which is 1/2, x, which is 5, plus b. So 6 equals 5 over 2, or 2.5, 5 over 2 plus b. And now if we want to take and subtract, we're going to go 6 minus 5 over 2, which is 3.5, or 7 over 2. So we subtract 5 over 2 from both sides, subtract 5 over 2, subtract 5 over 2, and we get our b value to equal 3.5, or 7 over 2. So our equation is going to be y equals 1/2 x plus 7 over 2. Now the question asks us to put this in general form. And so if you remember, general form means we cannot have any fractions. So we need to get rid of the fraction. And that's going to give us 2y equals x plus 7. And the other thing that we need for general form is we have to have a positive x. So we're going to move everything left or right to get that positive x. And so we're going to subtract 2y from both sides. And our final equation is going to be x minus 2y plus 7 equals 0. So the function notation is the new piece. I just wanted to give you a chance to review something from the last unit. All right, guys. Thanks for watching, and ask me if you have any questions in class, and we'll see you soon.